Hi, ladies and gentlemen. Welcome to my presentation. My name is Linjun and I'm from Southern University of Science and Technology, China. Today, I'm gonna give a talk on metric for evaluating normalization methods in multi-objective optimization. My presentation will be divided into 5 parts. I will introduce the background first and discuss the existing metrics and their limitations. Then I'm going to present the proposed metric, show some empirical results, and draw conclusions in the end. Now let's start with the first part, background. Here shows the formulation of a multi-objective optimization problem, MOP, with M objectives. A real-world MOP has several common properties. The first property is that the M objectives are usually conflicting with each other, such that no single solution can minimize all objectives simultaneously. A set of trade-off optimal solutions called Pareto front shown here are usually obtained. And also the second property is that the M objectives usually have different units such that the objectives are differently scaled. As shown here, the objective range R1 of the first objective and R2 of the second objective are differently scaled. Various multi-objective evolutionary algorithms, MOEAs, have been proposed to search for the Pareto front. Here shows the framework of a typical MOEA. In order to deal with MOPs with differently scaled objectives, a normalization method, which is an independent algorithmic block, is almost always used in an MOEA, such that the environmental selection is properly performed in the normalized objective space. Since the ideal point, the nadir point, and the objective range are usually unknown in the real-world MOP, so as you can see here in the normalization method, we estimate the ideal point, nadir point, and the objective range at every generation using all the examined solutions here. And then we normalize each objective using this equation. Different methods have been proposed to adaptively estimate the ideal point, the nadir point, and objective range. In this paper, we only consider some representative methods. For more normalization methods, you can refer to our survey paper, a survey of normalization methods in multi-objective evolutionary algorithms. For the ideal point estimation, it can be estimated by taking the minimum value of each objective in all the examined solutions at every generation. More efforts have been made on the nadir point estimation. These methods can mainly be classified into 3 categories: the straightforward method, extreme point-based method, and hyperplane-based method. The straightforward method takes the maximum value of each objective in a solution set, for example, the non-dominated solution set. And the extreme point-based method firstly identifies a set of M extreme points, and then takes the maximum value of each objective from these extreme points. The hyperplane-based method further constructs hyperplane using these extreme points, and then the intercepts between the hyperplane with the objective axis are used to calculate the nadir point. For the objective range estimation, we consider this simple method, that is, taking the difference between the estimated 2 points to calculate this objective range R. As normalization is a key component in an MOEA, many efforts have been made to investigate normalization methods. Now let's move on to discuss some existing metrics for evaluating normalization methods and their limitations. Existing metrics for evaluating normalization methods can be classified into these 3 classes. Let's talk about them one by one. The first category of existing metrics is that the estimated ideal nadir points are evaluated separately. And this metric, the error metric, has been widely used to evaluate the quality of the nadir points. and this metric calculates the Euclidean distance between the estimated nadir point and the true nadir point in the normalized objective space. Here R is the true objective range. However, this error metric is not a good metric for evaluating normalization methods. You can see in this equation, the effects of the ideal point, the estimated ideal point, is not considered in this metric. And also, this metric cannot properly show the effects of normalization. As illustrated in this figure, points A, B, and C are 3 points with the same value of the error metric, but they have completely different effects on normalization. Points A and D have different error metric values, but they have exactly the same effects on normalization. The second category of existing metrics uses the objective range to evaluate a normalization method. Ishibuchi et al. Plotted the estimated range for each objective. For example, here we plot the estimated objective range for each objective in the first 100 generations for a 3-objective problem. We can see that the major advantage of using objective range is that this objective range is directly related to normalization. However, it is very difficult to interpret this kind of plot, especially when the number of objectives increases. To show the variance of the objective range over generations, Chen et al. Proposed the norm of the objective range. In this equation, R prime is the estimated objective range, and R is the true objective range. This metric shows the closeness of the estimated nadir point to the estimated ideal point in the normalized objective space. Although this metric directly considers the objective range, it may not properly reflect the effects of normalization. As illustrated in this figure, points E and F have completely different effects on normalization, but the 3 points, E, F, and the true nadir point they net have the same value of this metric. Now we arrive at the third category of existing metrics. The algorithm performance is used to show the effects of normalization. In some studies, like here, the authors incorporate the normalization methods into an MOEA. The performance of an MOEA is then used to evaluate the normalization method. However, it is not easy to understand how the normalization methods affect algorithm performance during the evolutionary process. Now let me show you our proposed metric. Here shows the motivation of the proposed metric. Since the effect of normalization is based on the 2 points, that is, the 2 points cannot be discussed separately, we directly evaluate the effects of the objective range. Different from this reference, the first reference, which considers each objective separately, we consider all objectives at the same time. Although in the second reference, all objectives are also considered at the same time, it cannot correctly show the effects of normalization. So we hope that the proposed metric should properly show the effects of normalization. Here shows the proposed metric, objective range error, ORE metric. We calculate the standard deviation of estimated objective ranges in the normalized objective space. And we can see that the ORE metric measures the amount of variation of the normalized estimated objective ranges. And the ORE value is large when the variation is large, while the ORE value is small when the variation is small. Especially, the ORE value is 0 when the estimated objective range has the same effects as the true objective range. To demonstrate the superiority of the proposed metric, we do some empirical analysis. Here shows the experimental settings. We use the error metric, norm of estimated objective range, and the proposed ORE metric to examine different normalization methods. and we consider test problems with different shapes of Pareto fronts. We suppose that the current population is uniformly distributed on the true Pareto front. 100 reference points on its Pareto front are uniformly sampled to represent the current population. Here shows the results on a linear regular triangular Pareto front. As shown in this figure, ZA, ZB, and ZC are three nadir points estimated by the three normalization methods. And black points are solutions on the Pareto front. The three blue open circles are three identified extreme points by extreme points-based method. And the gray surface is the constructed hyperplane using the three identified extreme points. We can see that the three corner solutions are correctly identified by the extreme point-based method. The hyperplane constructed using these 3 points is the same as the linear Pareto front. The estimated nadir points ZB and ZC are exactly the same as ZA. This table shows the values given by the 3 metrics. We can see that the error metric and the ORE metric gives zeros to all the 3 estimated nadir points, meaning that all the 3 estimated nadir points are the same as the true nadir point. Although this norm of estimated range is non-zero, but exactly the same value is given to all the 3 points, meaning that the 3 estimated nadir points have the same estimation quality. These observations are consistent with the visual observations in this table, or in this figure. That is, all the 3 metrics can correctly measure the estimation quality of the estimated nadir point. These figures show the results on the linear inverted triangular Pareto front. We can see that the extreme point-based method fails to identify the 3 corners of the inverted triangular Pareto front. Instead, the points around the middle of each side is selected and identified as extreme points. This is because the closest point to each axis is selected as an extreme point. Interestingly, despite all this, the straightforward method and the extreme point-based method give the same nadir point. We can also say that the hyperplane passing through the 3 identified extreme points is much larger than the true Pareto front, and the estimated ZC is far away from the true nadir point. However, the 3 nadir points have exactly the same effect in terms of normalization. This table shows the values given by the 3 metrics. We can see that the 3 metrics give the same value for ZA and ZB, since they are the same. For ZC, however, each of the 2 existing metrics give a value larger than that of ZA and ZB, meaning that the quality of ZC is worse than ZA and ZB. These evaluation results are consistent with the quality of nadir point estimation. However, they do not show the quality of normalization, since the same normalization results are obtained from all the 3 nadir points. The proposed ORE metric gives the same value to all the 3 estimated nadir points, which is consistent to our observations. That is, all the 3 nadir points have the same normalization quality. Here shows the results on the irregular Pareto front. We can see that ZB is very close to ZA, although only one corner of the Pareto front is correctly identified, and the hyperplane passing through the extreme points cannot properly show the range of the Pareto front, and the estimated ZC is far from the true nadir point. This table shows the values given by the 3 metrics. The error metric and the proposed ORE metric gives 0 values to ZA, meaning that ZA is the same as the true nadir point, and ZB is evaluated to be worse than ZA and better than ZC by the 2 metrics. These results are consistent with the visual observations in these figures. However, if we use the norm of the estimated range, we can see that ZB is estimated to be better than ZA. This is inconsistent with the observation in this figure. Here shows a summary of observations. For the error metric, it can evaluate the estimation quality of the nadir point, but it cannot evaluate the quality of the estimated nadir point in the context of normalization. For the norm of estimated range, it cannot evaluate the quality of nadir point estimation, and also it cannot evaluate the quality of the estimated nadir point for normalization. But for the proposed ORE metric, although it does not always evaluate the estimation quality of the nadir point, it can always evaluate the quality of the estimated nadir point for normalization. Now let's conclude the presentation. In this paper, we discussed the limitations of the existing metrics for investigating normalization methods. We proposed a new metric called ORE metric for evaluating normalization methods. As demonstrated by our empirical analysis, the existing metrics are not suitable for evaluating normalization methods, while the proposed ORE metric measures the effects of normalization more properly. That's the end of the presentation. Thank you very much for your time.